Hello, Maker! Welcome to the Psychogenic Lab. You've got a custom FPGA circuit and want to give it a really easy way to update the configuration and function without clunky programmer hardware in your hands or on the board. Well, you're in the right place. Using the bootloader I'll show, you get a sweet way to update the system straight from USB, and it's so crafty that it doesn't cost you any hardware other than a USB receptacle or any space on your FPGA. Your projects can leverage every single cell. In the first video of this series, we created a custom FPGA PCB. Check that out if you're curious about the hardware side. Now, the target board could be anything as long as you give it some access to USB. In our case, we wanted something that would be able to be used standalone or fit on these tiny tape-out demo boards and have the same footprint as the ASIC carrier here, and be able to simulate the slow-to-arrive ASICs and have the same inputs and outputs and generally act as a drop-in replacement. Oh, and look at this. From imagination to reality. Built a few of these and they are sound. Huzzah. Now, this is an actual ASIC carrier board, and underneath, there it is, the custom FPGA PCB stuffed with its own flash and oscillator for standalone or demo board use. The important thing now is giving this simple custom FPGA module the smarts to let us update the bitstream with nothing but a USB cable. So let's talk bootloader. This is a wheel we don't want to invent. It's complicated and there's no need to do so. Uber hackers have already taken care of it. So the original plan was to use the TinyFPGA bootloader, which supports at least 6 different boards, and the FOMU even uses the Lattice ICE40 UP5K I'm using here, so I thought porting over would be pretty easy. I have grown to dislike the TinyFPGA bootloader. Getting it built and going wasn't too bad, actually. The TinyFPGA system is pretty smart and ideally uses programmable security register page stuff on the flash to store metadata. Now, I'm using the flash from the demo boards, which doesn't support this, which was an annoying start because it was being too smart and getting in my way. I worked around that and managed to set it up to appear as a USB device and everything, but I was really struggling to get it talking to the SPI flash after that. So I reached out to someone who knows more about this than I to figure out how to get the TinyFPGA bootloader working, and he said, don't use the TinyFPGA bootloader. Enter the Nitro bootloader. Sylvain Munot, aka TNT, did amazing work with the hardware mux that selects projects on the latest tiny tape-out chips. He's also got a lot of cool FPGA material under the Nitro FPGA banner. One of these repos is the NO2 bootloader. That's meant to allow DFU flashing to update not only the bitstream for the FPGA, but also the bootloader itself, and it should be good for at least all the ICE40 FPGAs. DFU, Device Firmware Update, is used by tons of devices to provide a standard way to do upgrades. The NO2 bootloader implements USB through a soft core and uses the same idea of 2 pins for the USB differential and that extra pull-up control line as the TinyFPGA bootloader I was originally targeting. So that's practical. The way it works is that there's a teeny bootloader system in there that keeps an eye on some pin during startup. If that pin's high when power comes on, it'll just disappear, configuring the FPGA according to your project. If it's low when power comes on, then as you bring it high, it sets things up with a whole system that handles USB and DFU and knows just what to do. Now that system looks relatively big, taking up about 3,300 cells on the FPGA, or about 70% of the space on the ICE40 UP5K. But it's only loaded when you've come up in DFU mode. Otherwise, other than sitting in the flash, it takes up 0 LUTs in the FPGA, and it's like it doesn't even exist. So you get the whole bootloader and DFU thing without it actually costing you any space when your projects are running. Very neat. It does this magic by segmenting your flash memory to load up a little stub that decides what's really going to happen depending on the boot pin state. Then it wipes itself out, setting up the FPGA from one of the image slots, either the firmware update system or your stuff. So the documentation is fine for building a supported image as is, but we want a fully custom thing. Based on other projects in there and some experimentation, here's how I got it working. A bit of this is guesswork, but hey, it's working. So let's see how to do that. Clone the repository with all its submodules. I'm using my own fork here. Now get in there and you'll find lots of stuff. Inside Gateware ICE40 stub data, there are a bunch of pin configuration files. PCF are a standard way of abstracting the specific pin mapping for a given FPGA platform from the project itself. If we look at the config for the FOMU, you can see a bunch of set IO directives with a name, and it maps that to the actual package pin. Not the logical name or anything like that, the pin. The only IOs really required here are the 3 USB pins, the SPI flash pins, and a button. Some input used to tell it when to boot in update mode, because that's not what we normally want to do. If we take a look at the schematic, you can see the SPI is just standard connections, the USB is over here, and I'm reusing one of the project select pins for the boot button. So create a file called top-yourprojectname.pcf. Now here's my own config file. For reasons described in the previous video, I'm using an external clock at an unfortunate 20 MHz rate that also happens to be on pin 20. If you have a choice, use some fraction of the 48 MHz USB wants to make things really clean, like 12 or 24 MHz. I've got the SPI and USB set to the pins on the SG48 I'm using, along with my repurposed Select 0 pin as the boot button, with an internal pull-up applied here, and that's that. Now your boot button should make that input go low when you want DFU mode, and otherwise be high during power up. By adding the pull-up directive here, you're setting things so that even if nothing is connected at all, it will boot into normal mode, which is nice, sane default behavior. Okay, the pin config is set, but the bootloader needs a bit more info to work. In ICE40 RTL boards.vh, there are conditionals based on the board name that do extra setup and flag tweaking. Some use mostly defaults, some have RGB LEDs, which I really should have added, some override the PLL configuration with explicit values. So you add an else if using your board name, all caps with underscores replacing dashes. Now we want to use the PLL to get that 48 MHz and base it on our input clock. But here I've got 20 MHz, so we need to figure out the values to give the system. A program called IcePLL will help us with that. You can just give it your input frequency and your desired output, and it'll tell you what to set and how far you are off the mark. So this won't be too bad. I just plop those values into the boards.vh file. Now that was boards.vh somewhere under ICE40. There's another different boards.vh file under ICE40 stub, which isn't confusing at all. In there, you've got more else ifs with similar but different defines. I think the ICE40 is for the bootloader USB softcore thing, which is why we have the generated 48 MHz in there, and here this may be for your actual project. I don't know. I just did the same as the other boards and put in a has USB, and that's it. Copy over the PCF file to ICE40 as well. Other projects have the basically same PCF, but without the pull-up specification, so I'm removing that here. I don't know about this. Anyway, with those 4 tweaks, we're done. You'll need a RISC-V cross-compiler and Yosis for this stuff to work. Details for getting those, if you don't have them already, are in the NO2 bootloader repo. So just in case, I'm calling clean here. The important thing is that the board variable is set to the board name you chose, same way you wrote the PCF file name without the .pcf. Then the actual make call looks like this, and it just goes and goes for a bit and goes and goes, and then it's done. The bootloader bin file is everything the board needs. Just need to get that into the flash somehow. Bit of a chicken and egg problem here. Your choices here are get your vendor or whoever's doing the PCBA to pre-program the flash before assembly, or if, like me, you are the assembly house, use ye olde programmer this one time to get it on the board. You can use headers if you have them, a dip clip if you don't, and to actually flash the memory, use something like the Tigard, or you can even repurpose an Arduino or a PiPico using Pico Serprog. However you do it, once it's done, you'll never have to do this again thanks to the bootloader. Now, let's see it in action. So I set up the button on the selector dip switch here to be low, and I plug it into the laptop. Now with power applied, let that button go high, and we should be in DFU mode. With Linux, the easiest way to play is with DFU util. The -L option lists attached devices. So after coming up in DFU mode, listing shows us 4 alternate devices to address. Alt 2 and 3 are dangerous, as they're related to the bootloader and are for updating that. The one we'll care about most is Alt 0, where we can shoot off our project bitstreams. There's also a slot for firmware. Let's give that a shot. Here I've prepared a little system that actually uses the select switches to change the behavior. This setting lets you clock an input and see the count go up. And this one prints out a little message to the 7-segment display. And this one auto counts. Neat, all right. You may have noticed I was using sudo to access the DFU device. That's annoying, so you can grab the USB vid and PID and do the usual things to give yourself rootless permission to access. Now, I like having access to all the DFU devices all the time, but you can force yourself into a tight spot where you scrap the bootloader and need to go through reburning the flash memory with wires and So if you want to safeguard against that, and we sure do when it comes to putting this board into high schooler hands, you can actually set it up a bit more. If your SPI flash supports it, and it likely does, you can configure a flash lock in the ICE40 stub boards.vh file. All the W25Q whatevers use the same little sequence, so I copy that over into my else if section. Okay, I rebuilt and burned that, and now putting it into DFU mode only shows the 2 normal endpoints for updates. Now you might still want to occasionally update the bootloader itself though. Sylvain has you covered there too, though, because if, when you're powering up in DFU mode, you twiddle the boot pin low-high 4 times, then all the alternates reappear. Nice. Okay, extra credit for those who really want the custom experience. There's a file up in firmware called USB string DFU, and you can add your project name as a key to the hash and some nice description string. If you've done that, then when everything is built, the USB product string gets set to whatever you put when booting into DFU. It'll show up in places like LSUSB and somewhere, I assume, under Windows, which makes for a very nice touch. So now we've got a custom FPGA board and a smashing way to get our project bit streams in there. This project can be any Verilog or Amaranth or whatever you want to run. In this case, I wanted an easy way for people to forget about the I/O mapping and also to have a way to bundle multiple tiny tape-out projects and switch between them, just like the real deal ASICs. So I created a little framework that lets you just focus on what you're doing with the inputs and outputs and group it with other modules. Then I created a bunch of samples, some of which you saw earlier. If you're curious about that, let me know in the comments and I'll do a video showing how I abstracted the platform details and such. Also, please let me know if this was useful to you in the comments or with a like. Good luck with your own custom FPGA circuits. Happy booting. Thanks for watching. Cheers.